And then there are two papers on pseudo-valuation domain. And let me remind you with the definition, you let R to be an integral domain with a quotient field K. And if every prime ideal satisfy this condition, whenever you have x, y in Q, Q is a prime, and x, y in Q for some x, y in K, then x in Q or y in Q. This class of integral domain is studied by many algebraists, including myself. And definitely pseudo-valuation domain is a valuation domain, but definitely not every valuation domain is a pseudo-valuation domain. Okay. In 1991, D.D. Anderson and Muhammad Zafrullah, in this paper, almost Bizu domain, introduced almost valuation domain. And what's almost valuation domain? Here is the definition. R is integral domain with a quotient field K. Then R is called almost valuation domain if for every x in K there exists an n. N depends on x, where x to the n in R or x to the minus n is in R. Okay? And for a recent article on almost valuation domain, I mentioned here 4 in 2015. Okay, so what's natural? We have valuation domain, then pseudo-valuation domain. Now we have almost valuation domain. So maybe it seems to be natural that somebody will study pseudo-almost valuation domain. And this is what I did in, let's see, yeah, here is it, on pseudo-almost valuation domain in 2007. And the definition, if you take R, the integral domain with the quotient field, if every prime ideal satisfy this condition, whenever you have x in K, there exists a positive integer n, where x to the n in a Q or x to the minus n, A is in a Q. So that's the definition of pseudo-almost valuation domain. And of course, almost valuation domain is a pseudo-almost valuation domain. But in that paper, I have many examples where of pseudo-almost that are not almost valuation domain. Okay. Let me remind you with this definition, if you want to follow my talk, I think you need this definition here. What we here, first thing we fix an integer n. So n is a positive integer bigger or equal to 1. And we define n powerful ideal. What does it mean? If whenever x to the n, y to the n in I, for some x, y in K. Remember, K is the quotient field of R. Then x to the n in R or y to the n in R. And I, we call it n powerful semi-primary if whenever x to the n, y to the n in I, for some x, y in K, then x to the n in I or y to the n in I. So n powerful semi-primary we require the x to the n to be in I or y to the n in I. Where n powerful, we require x to the n in R or y to the n in R. The concept of powerful ideal was studied by myself and Evan Houston in this paper in 2002. So now we come to the definition of n-pseudo-valuation domain. Here we fix an integer n bigger or equal to 1, and we say R is n-pseudo-valuation domain if every prime ideal is n powerful semi-primary. And so n pseudo-valuation domain means every prime ideal is n powerful. N powerful is here again, that whenever you have x to the n, y to the n in I for some x, y, and k, then x to the n in I or y to the n in I. Okay? Clearly, if n equal 1, then pseudo-valuation domain is 1 pseudo-valuation domain. Okay, first thing, here is an example you can stare at. This example justifies the work we're doing. This ring R is not a pseudo-almost valuation domain, is not pseudo-valuation domain, and is not almost valuation domain. However, this ring here, this integral domain, is for pseudo-valuation domain. Okay? All right. So with that, here is a connection between n powerful and n power. If I is a prime ideal with a quotient field k, then there is no difference between I to be n powerful semi-primary ideal or just I is n powerful. Oh, my mobile, I put it off. Sorry. Okay, so there is no difference between the two definitions. Here are some properties of n powerful semi-primary or n powerful ideal. Like if you start with two prime ideal, one of them inside the other, P is inside Q, then Q and Q is n powerful semi-primary, then definitely P will be n powerful semi-primary. And also we get similar result. This is true for pseudo-valuation domain, for pseudo-almost valuation domain, and this result is true for almost valuation domain, which is what? If R is an n pseudo-valuation domain, then R is a quasi-local domain. And also, that's also true if you have an integral domain that is an n pseudo-valuation domain. Here is a complete characterization. You only need to check for one maximal ideal, and you make sure that this maximal ideal is n powerful semi-primary ideal. And remember that n powerful semi-primary is the same excuse me, as n powerful ideal. So you get similar result, because we know that pseudo-valuation and integral domain is a pseudo-valuation domain, if only one of the maximal ideal is strongly prime. Here we don't use strongly prime, we use n powerful semi-primary or just n powerful ideal. Okay, so let's skip powerful, just normal n semi-primary. So here we choose the x and y in R. Remember, if I add powerful, then I choose x and y in K. So here's a definition of n semi-primary. You're going to see that why for a minute. In general, if an ideal, look at this theorem, if I is n semi-primary, then I is m semi-primary for every m bigger or equal to n. Okay, remember the difference between n semi-primary and n powerful semi-primary has to do from where you choose your element x and y. For powerful, we choose them from the quotient field. So why do we need to consider that? Because remember, by the previous result, if a maximal ideal of an integral domain is n powerful, then R will be n pseudo-valuation domain. So the question, if I have two pseudo-valuation domains, does it mean it is 3 pseudo or 4 or 5? Unfortunately, the answer is no, or maybe fortunately, because you cannot generalize this theorem to powerful. So what that means, if I have an ideal that is n powerful ideal or n powerful semi-primary, and you choose m bigger or equal to n, then the ideal need not be m powerful semi-primary. So we answer the question maybe some of you have in mind. Does two pseudo-valuation domain imply 3 or 4 or 5? Because of that result, the answer is no. Okay. Here are some of the examples also. You can stare at that. This is an example where n powerful semi-primary need not to be m powerful semi-primary for some m bigger or bigger than n. Okay, so what also we know? Well, remember the definition of divided domain, meaning if you have a prime ideal and you choose an element x outside the prime ideal, then Q has to be inside the ideal generated by x. This is one way to think of divided. So what do we mean with n divided? It means if you have a prime ideal, remember we fix an n. So it will be n divided prime if x to the n divide p to the n for every x outside p and for every p in the prime. And the ring will be n divided if every prime ideal is n divided prime ideal. And of course, if n equals 1, then this is just the divided rings in the sense of Garth's Badawi definition. Why did I mention that? Because it's known that pseudo-valuation domains are divided domain, meaning one divided domain. So if you have n pseudo-valuation domain, then R will be n divided domain. and the set of prime ideal linearly ordered. Of course, this theorem, no comment. I mean, the proof is trivial. If the ring or the integral domain is root closed, then there is no difference between pseudo-valuation domain and n-pseudo-valuation domain. That should be clear, I think. Well, then we start looking at what about if P is a prime ideal and R is n pseudo-valuation domain. What can we say about the quotient R mod P is n pseudo-valuation domain? Okay. Here is I remind you with almost valuation domain. What does it mean? There exists an integer bigger or equal for every x in k. There is an integer where x to the n in R or x to the minus n in R. So what about, remember in this almost valuation domain, the n depends on x. Here we fix an n and we call it n valuation domain if for every we have x to the n in R or x to the minus n in R for every x in k, as it's written here. What is the connection? This is the connection. If you have R is an n pseudo-valuation domain, yeah, and you have an overring of R where 1 over S in V, then V has to be n valuation domain. Okay? And this is similar here. We get some n pseudo-valuation domain when you localize R at some non-maximal prime ideal P. If P is non-maximal and you localize R at P, and you know that R is n pseudo-valuation domain, then this localization will be n valuation domain. And we give a complete characterization of when every, okay, let's see, yeah, here we go. If you choose an n bigger or equal to 1 and R is quasi-local with maximal ideal m, the following are equivalent. R is an n pseudo-valuation domain. The integral closure of R is a pseudo-valuation ideal with this maximal ideal. This ideal is maximal ideal of the integral closure such that this is a valuation domain. Okay? And there are some other characterization. This ideal kind of interesting. You look at the ideal generated here, look at the definition, A and M, x to the n, x in k, such that x in k and x to the n is in M. And we define, this is a set, need not to be an ideal. But then in the theorem, we let I to be the ideal generated by this set. Then we have another characterization in terms of n pseudo-valuation domain. If I take Vi colon I, remember I is the ideal generated by the set ANM here. Then, of course, if you look at that, if you let n equal 1, then you have R is one valuation domain. if and only if V will be M. V I will be M. If N equal 1, then I will be just M. And all of us know that R is one pseudo-valuation domain if and only if M column M is valuation domain. So this is true for any N, but here we have to be careful how to construct A and M. And this A and M, by the way, we don't have time, maybe I run out of time, does not need to be equal to M at all times. In fact, we have examples, we have many examples where this is different from the maximal ideal M. Do I have time or I stop? I think I just, maybe I run 2 minutes. I'm not sure.
Yeah, we can give you 2 more minutes.
Okay, thank you. Maybe I will answer some of the question if you have here with the examples. Like here is an example where if you look at this R here, then R will be N pseudo-valuation domain if and only if N bigger or equal to 2. Where this will be N valuation domain only if N is even. Okay? And here is also another example of N pseudo-valuation domain where the ideal generated by A and M is the proper subset of M. Because I think I told you this ideal generated by A and M need not be equal to M. Here is an example of such N pseudo-valuation domain where this ideal is different. And here we have other examples where what we're looking at is almost valuation domain, but is not N valuation domain. Kind of interesting. So almost valuation domain does not mean N valuation domain. And I have more. And if you are interested, here is you can get the full table for free by going to this web page. All right, and I thank you all.
Thank you. Thank you, Ayman, for your talk. Are there questions in the chat? Are there any questions in the audience? So if this is not the case, let us thank Ayman again. And I would like to thank Ayman and all the speakers, and we close this morning session. Thank you.
Thank you.